Hey guys, thank you very much for the invitation, David. Yes. So, yeah, I'm Harry Lee from Civil Environmental Engineering and Water Research Center. So, title of talk is the recent development in inverse modeling data simulation in hydrology. But usually, I try to emphasize inverse modeling, definition of inverse modeling, how we tackle that, especially for the some when we have the high dimensional estimation of some sort of parameters of the model, and also if we have a lot of observation. Okay, so typically in science and engineering, we usually do the modeling because we don't have analytical solution to the underlying phenomena in many cases. And so this kind of the prediction or simulation is there is some kind of assumption of the governing equation because you took a lot of the PD course, OD, and numerical courses. So there is some sort of the governing equation, and if you cannot find the analytical solution, you have to resort on the numerical solution with some approximation with finite difference, finite element, boundary element, and other kind of schemes. Then um, so whole assumption is basically you have very confidence in the carbon equation. So for example, in my case, I usually work on the uh, groundwater engineering and subsurface. So subsurface usually deal with the some movement of the groundwater and also the trace contaminant in the groundwater, and it requires permeability or soil conductivity, hydroconductivity, where there should be some sort of the this kind of the heterogeneity. So, for example, in the right flood, so there is a red spot. We have the some permeable um, soil structure, and blue is more like impermeable, like clay or other kind of layers. And then so based on this kind of heterogeneous formulation, which is governed by some geology professor processes over the time, and water is following its path based on this one. And because we don't have any kind of analytical equation to how to measure, how to um, simulate the movement of water and some contaminant, and we requires carbon equation. In this case, some elliptic or probability equation is used to simulate this one. And assuming that the flow is from the left to right with some uniform, and we are injecting some displaced to a dye or like some spilled contaminant, nitrogen or some oil components, and then so if we know perfect information about the boundary, domain size, and the soil distribution, and a kind of the PDE, then so you will end up with this kind of simulation region. So basically, the bottom left one is the flow field potential. So the perpendicular to this kind of contour is the direction of the flow. And because we assume that we injected some kind of tracer here, the tracer concentration is moving like this, following this high permeability zones. But the problem is, we really don't have all this kind of information, okay, in practice. So usually carbon equation. So there's always some kind of modeling error. So some PD or the groundwater equation may not work for every general situation. Okay, and this particular PD is assumed that we have 2D domain, so depths integrated from the 3D, and also this aquifer is surrounded by some impermeable on top and bottom. Okay, and also the in the carbon equation, hydroconductivity is carbon equations coefficient, PD coefficient, and we really don't know about this one because we have to measure every coefficient in every position. So in subsurface engineering area, it's really hard and very costly to measure all the soils in the ground because you have to drill. And domain extent and boundary condition, initial condition, they are all uncertain in any cases. So what people usually do is run the calibration, inverse modeling, or the history matching and other kind of things. And so it's basically given the information. So usually our previous settings, so let's say we have some kind of very luxurious environment that that we can measure at this point about the pressure or hydraulic head and also concentration at these wells, then we probably have some sort of information about the time series information about the subsurface problem. Okay, still we really don't know about this kind of the true permeability distribution, so which is PD coefficient in distributed domain. So using this sparse information, even this, I said that this one is the luxurious, settings, but still to get to know about the permeability at every pixel uh, is really hard to predict. Okay, so what people usually do, or just the terminology for this kind of process is inverse modeling. So in general sense, applied mathematics. So usual numerical modeling, or let's say this is a forward way that we have some kind of input data, then use the physical based model, then we'll get the distribution of the state or output at the every grid cell of the domain. And I mentioned before, the measurement is just a sparse subset of this output. So you use some kind of output, and usually output is dominated by or contaminated by some kind of error. So you have noisy measurement of sparse set, and try to invert this relationship and do the estimate the unknown variable. In this case, our concern here is the permeability distribution. Okay. So this is so-called inverse relationship, inverse problem. And so what we usually do is have the observation, sparse observation, and try to estimate this distribution of the model parameters. In this case, this is steady state problem. If it is some kind of a dynamic problem or evolving problem, you want to just keep track of change of this state variable S in this case. And this inverse problem is, you say that this is very challenging because first, usually number of unknowns we would like to reconstruct is the number of the grid cells in the numerical model, but number of observations is much smaller than the one. And this is called underdetermined problem. And so usually this is the underdetermined problem has infinite solution, which means that you can actually try different distribution of the S, then you may be able to reproduce the observation exactly same with different number of observations. So there is no unique solution in this case if there is a solution exists. And also the problem itself is ill-posed, which means so in the forward modeling, so if you learn about the finite element method and other kind of things, they are very stable. So little bit of change in the input parameter will actually result in the very small change in the output parameter in this forward map. But in the inverse map here, if you have any kind of little bit of change perturbation in the measurement, then the variation in the original input parameter can really large, can change a lot. Still, it actually satisfied a measurement reconstruction. So this is the ill-posed property in the sense of Hadamard. And so underdetermined ill-posed is some kind of challenge of the inverse problem. And this is very, you have to actually deal with it carefully to have some sort of some determined solution, some unique solution or subset solution that actually makes sense for your application. And another thing is, so I did not mention about the uncertainty. So should be uncertainty in the model and data. So your governing equation, your physical equation you want to calibrate is definitely lose some kind of information or uncertainty because of the resolution that is supported and resolution that target. So because discretizations may be coarse, while you are just looking at the very, very small, tiny detail at the fine scale grid. And data itself, if you just acquire data, and usually the gauges has some sort of observation error and other kind of errors, and you have to count uncertainty. So usually in the statistical inverse problem, stochastic inverse problem, you not only you have to provide not only the some kind of best estimate the solution of the this state S, but also the range of S or uncertainty of S in the final outputs or report. See. Okay. Okay. So let's just know this example. So the one subscriptive problem. So there is a true conductivity cases. Just you and with this conductivity, you can generate the data at the pressure at the this location and add some kind of noise. And with this data, and also you have some kind of confidence about your numerical model. And so typical inverse solution is looks like this. So basically, this is some kind of smooth version of the true conductivity or image underlying process. This is because pressure data and the carbon equation, in this case, elliptic equation, is the has some kind of information about global trend. So the reconstructed field is usually have some sort of smooth field because it only have global trend information and loses some sort of detail. And if we can add more data sets, like a trace data. So now the trace data is governing by the Ovexan equation, Ovexan and diffusion equation. Ovexan equation is, in this case, the carbon equation. The information is propagated the upstream to downstream. So it's not giving you the, does not give you the global information or trend of the underlying process, but gives some sort of the details around the measurement area. So combining different kind of the future different kind of information will actually enhance the inversion estimation result, and so yielding like this kind of was quite good estimation of the underlying process. So this is different types of the information or the data information, and so maybe we can talk this one for later in the seminar or other times. Okay, so definitely, so you probably want to do some kind of prediction or forecast based on the estimated parameters, and this is like this. So only has data. So this flow information does not contain any kind of transport information. So this is only you can get with the different process simulation. But if you include the different types of data, definitely it is much better prediction of the underlying process. So this is inversion, and data assimilation is like, it's inversion is more like, they are very similar to data assimilation with batch data inversion. Inversion usually refers to some process to have all the data set you acquired during the process, and then use all the data set to capture data. And data assimilation is more like, focus on the forecast. So more like a real-time forecast. So if you have the some sort of the current knowledge and you get the some real-time information, you update the with the current information to have a much more better performance and forecast. And I would like to really restrict this presentation to the inverse modeling, while there is some I will show some example about the data assimilation. And data assimilation, there is some sort of the specific concern about that. Usually data assimilation is more real-time data collection and forecast. Maybe people prefer the reliability of the algorithm over the accuracy of algorithm. So even if just assume that you have really good data assimilation method that guarantee the accuracy of the forecast, but sometimes maybe like 1% or 2% times it actually diverges or just stop on some instances. Then people might not really like this kind of algorithm, because like the weather forecast or something like that, you want to just have the get the streaming of data and do the reliable forecast over time, even if you actually have the little bit inaccurate solution. So in data assimilation, or probably the reliability and stability of the algorithm or convergence algorithm is quite important than inverse modeling. So inverse modeling is basically one-time batch data assimilation. So maybe it is a 1 to 6 very accurate solution. Okay, I don't want to just put mathematics here. So usually common approach to account for the uncertainty of the underlying process in inverse modeling is using the Bayesian algorithm. So Bayesian is basically, it's one way to interpret your probability. So you might heard that the frequentist and Bayesian type of the interpretation. So you can interpret the probability or chance uh, with this kind of viewpoint. And many forecast problem, like the weather forecast, so whether it is rain or not tomorrow, is not suitable for the traditional classical definition of the probability. So classical definition of probability or frequentist probability is like, you just do a lot of experiment over the long run. So they will have just some kind of frequency of the occurrence, like it's rain or not. Then, so based on this frequency, you assign the probability. But now the problem is, so tomorrow's rain or this specific application, subsurface application, subsurface engineer application, we really don't have a lot of data. So in that case, the probability can be interpreted as the state of the knowledge, and state of this knowledge can be propagated with current information to have better accuracy or wider, again, more small uncertainty, more wide uncertainty. In that case, Bayes rule is really important, and then basic assimilation machinery. So which is basically, so you have some kind of state knowledge here, prior knowledge, and if you have the more information, then you will get a more updated knowledge. So that's the one sentence summary of the Bayes rule. And typical inverse problem data simulation problem, especially in earth science. So we are based on this Bayes rule and to account for uncertainty. Okay, and then so at the end of the day, so using the parameter estimation, inverse modeling, state estimation can be summarize this kind of the diagram. I don't want to just look into that, but basically the parameter estimation, you just have the prior information about your underlying surface. So this prior information can be like in subsurface problem. Okay, so you have the permeability. You can include the your state of knowledge into the some prior knowledge there. Like permeability is not negative, not zero. So it should be positive first. Second, so uh, soil type, one location of soil type is very correlated to the neighboring soil type. So you may assume some kind of spatial correlation between the 2 points or 3 points or other points based on their area. So this kind of information can be encoded in your statistical model, and starting with this prior information, and you can update with the observation, then you will get the final solution. And data assimilation is basically same, but there is a stream of data you update over and over for mostly for forecast and also estimation of underlying parameters. Okay, so very brief summary of the inverse modeling and data simulation, just in like 5 slides. Okay. So what are challenges? So we have really good algorithms out there. You can download many the packages in MATLAB, Python, C++ to do uncertainty quantification, inverse modeling, and data simulation. But now the problem is the high dimensional problems. So basically, idea is because of the advancement in the sense technology, so you have a lot of sensors right now. So even remote sensing and satellite images and geophysics and other kind of data sets. So now you access a lot of data and a lot of data streaming or streamings that can be used for your um, the parameter estimation. And also the second thing is the supercomputer and other kind of computation or enhancement. So now you have the some kind of good computation resources. For example, so your common desktop with the Intel Core i9 core is basically probably same as the top one supercomputer speed at around 2000. Okay, so now you have this kind of capability in 20 years ago or 15 years of the ability, but now you have the access, you can access cloud computing, so with really low cost, and also high performance computing clusters and other kind of things. Definitely you can have the very good resources quite close to the top one supercomputer these days. And so you have time to run your numerical model or the model with this kind of the good computational resources. Then your discretization and your parameter or number of parameters can easily um, 10 million or 100 millions for your problem. Then once you just work on this kind of very good complex numerical model, um, and once you just develop this model and wanna just try to apply to this one to the real world case, then you realize that you don't have any kind of information about your coefficient for specific application. Now you have to do some sort of the data simulation and inverse modeling to estimate the parameters. Then, so you have to estimate the 10,000, 10 million, or 1 billion parameters for with the 10,000 or 100,000 observations. Okay, and so if you're familiar with the so this probably you may think about this one is very expensive processes, and also if you're familiar with this data simulation and very basic application for data analysis requires some matrix multiplication inversion in the update of the parameter. And this actually requires a lot of computer operation and storage. And second, and also typically the inverse modeling or data simulation requires at least 100 or thousands numerical models. Even if your numerical models can be parallelized under the supercomputers, but still it will take order of 10 minutes or order of hour, order of day. And so 100 or 1,000 or 10,000 numerical models may not be feasible in your cases. So how can you deal with this kind of challenges? Okay, so basic idea is one advancement in this area is try to make the all of this multiplication and storage as scalable as possible. So so here scalability, I mean by some kind of linear scalability, where if you just increase the number of the parameters or number of the grid cells, then your computation cost only at most increase linearly. So this is so-called linear scalability. So in many cases, many algorithms in computation probably quadratic scalability and order n square or cubic scalability, but what we really want to do is the linear scalability. So you can actually look into this kind of the plot here, and then some of the my state art multiplication problem. So let's say the 10 to the 4 degree of freedom matrix, so 10 by 10 matrix times some vector would only take about the less than the 1 second. But if this is the have the quadratic scalability, then once it start following the quadratic line, then 10 to the 5 will become like the 100 second, 10 to the 6 degree of freedom matrix can be 1 hour, more than 1 hour, and so billion element of the matrix can become like computation of the some million seconds or something like that. Okay, so what we really want to, people really wanted to achieve is just linear time scalability, because we are just have a capability to adding more and more cluster and computers and do the parallelization. So linear scalability maybe that's some kind of good thing. So we would like. And also another thing I want to mention is like for matrix inversion. So I just talk about some matrix algebra real quick, but the computation time of the matrix inversion is dependent on the condition number of the matrix. So condition number of matrix is the they're like think about the range of the matrix of the Bell matrix outputs. If you increase the number of the size of the matrix, then this condition number or just change a range of the outputs can be really large, and this actually requires more and more um, computational resources, not the linear scale, but the like quadratic or the cubic scale of the like operations, computation operations. So probably we want to have the really, really good method to reduce this one to the linear scalability. Okay, just a quick review of the matrix linear algebra. It is simple. So like um, let's say I would say so in many engineering application or even science application, 99% of the application is based on the linear or linearized method. Okay, so everything. So if you just look into the all kind of the computer operation other things, they are all based on the linear algebra and matrix theory. Okay, and their operation is linear. Everything is based on linear, and the linear theory is just they have been advanced over several decades. So we know that a lot of the package, computer packages, and can be useful for this kind of operation. And if your process is non-linear, and usually you are just linearize it, so make it successively linear problems and solve it. So everything is based on the linear. Then the basic operation here is you just have the matrix and vector, and at the end of the day, you will solve for PD problem, optimization problem, other things, and you will solve the AX equal to B. So A and B is given, and you want to solve the find the X. And this problem arises any kind of problem, PD, estimation, optimization, and usually this kind of approach requires storage. So you can think about the order n square. So this is n by n matrix, then n square number should be the saved in your hard disk or any kind of the storage devices. And multiplication. So a times b, like a times b. So this also requires n square addition and multiplication. So basic operation has the n square scalability. And this is the core algorithm. So solving linear system. So this is every PD problem, numerical problem can be come down to this kind of formulation, and you want to just find the X. A is from your material property, like in the subsurface engineering. So the element is your soil conductivity value, and B is probably related to your recharge or input source, and also the boundary condition and other things. And this computational cost usually requires order n to order n cubic. So sometimes it is really expensive. And so if you understand the problem and implementation, it can actually reduce the very fast implementation. Okay. So what people usually do, try to do the reduce the computation cost is so let's say decomposition or so-called compression. Okay. And this some matrices arise from the like boundary element problem or estimation problem. This A is dense, which means every point element of the this matrix is non-zero. So you have to remember or store it on the hard disk with these non-zero values. If you have zero values, probably you just check the location and then just get rid of this value, then save a lot of cost. And what people usually do with the dense matrix is try to compress. So you probably heard the SVD, eigenvalue decomposition, and other things. So this is basically an idea just in the process of compression of this A matrix to a certain small subset of the solution space, subspace, I would say, subspace. So if you just look into the A matrix and have some kind of features, you just extract features and you only just save features. So that's the ideal. And then you disregard any kind of the unrelevant and very small scale information. And like this is, can be understandable, very easy to grasp the concept for the image processing. So example is like, for the image compression. So you have this kind of original image of Mana 4, which has the 33 megabyte. And so like using the previous mentioned data compression strategy, if you just only have the 50 salient features, and you have only 1 megabyte of the image with the all kind of information is still there. So you can actually see the blurry some features of the Mana 4 because of the 50 term is not enough for the capture all the salient features. But if you just have the only one term, 100 columns or features, then so with 2 megabyte of image, actually, so from human eye, it's really hard to tell the distinguish between these two images. So this kind of decomposition, compression, kind of strategy is quite, easy or just, very, very convenient for storage of the matrix or just large numbers. Okay, and this is quite widely used in the some kind of the image processing or signal processing. Okay, so and also if you just only have the 100 features, 100 columns, matrix times vector or matrix by matrix is much easier because you only deal with this small number of the columns or features. And so, and if you can actually compress this image or matrix, then you can probably achieve the linear scalability or even sublinear scalability. Okay, so but why is the problem with this kind of compression technology? And the problem is the pre-processing step. So decomposition or compression, usually the cost is the order n cubic, okay, which means if you just increase the size of the image or matrix by 2, then your computation cost becomes like 8 times more, okay, or storage is something. And also some matrix can be compressible, other matrix cannot be compressible. Like, you have really, really high features of the high resolution features in the image, then you have to actually honor all the features and to reconstruct this image. So the idea of the linearly scalable algorithm for this kind of the matrix storage and matrix multiplication is so-called hierarchical matrix or first multiple method. So the idea is basically simple. So instead of working on this really large data, so you just look into some small subset of matrices or some portion of the image, then you are just hierarchically divided this matrix and just looking at this, investigating this small subset matrix and do the compression if possible or not, or if it's not possible, just leave it there. Okay. So let's say you start with some kind of data matrix or some matrix is with the red one. Then, so let's say for some reason, this one is not compressible, okay, or just really inexpensive. Then you are dividing this one by just quad tree types. Then looking at this sub matrix and whether you have the can compress or is expensive or not, you can check and do it again. Now, usually for some matrix, especially for the matrix like Gaussian matrix, Gaussian corner matrix in data simulation, so off diagonal block is more like expressing the compression correlation between the one point and another point far away. So they have not many information or I would say no correlation. So in that case, they have no correlation means it can be compressible. So there is no high resolution features. So you can actually compress it really easily. So and also you are just operating this kind of compression technology on the subblocks. So it's also very much cheaper than the comparing to the entire block compression. So do it again, usually this one and again. So at the end of the day, so there is some kind of doing this hierarchical separation. There is some kind of portion that you can actually compress or other portion you cannot compress. And so this pre-processing step is very efficient and it does not take a lot of time, and you can just put some effort over this pre-processing. Then you can actually save this dense matrix, very high information matrix into the some sort of the compressible block and non-compressible block. And so this red non-compressible block, you just save the with real numbers. This other blue compressible block, you just use the only leave the some salient features. Then matrix multiplication storage you can probably achieve some sort of the order and scalability or linear scalability. And so using this kind of techniques and you can accelerate the dense matrix algebra. Okay. Uh, so this is another example, like the okay. So the recently I wrote some kind of software based on this technology, and it achieves the matrix times vector operation very quick, like 10 to the 7 element matrix with one column of 10 to 7 vector. It only just take about less than a minute or something like that. So it's very cheap. And another thing I like to mention. So usually all kind of the data assimilation solution and inverse modeling solution can be projected onto the some subspace or the smaller number of the salient features. Okay, so usually in the typical data assimilation problem, so you have prior knowledge. If you just find the prior knowledge space and salient features, then only you keep the 50 or 100 salient features or the dominant features and project your solution onto this basis, then you only have the 50 or 100 degree of freedom or number of parameters to do the estimate parameters. Okay, so instead of just using the million or billion grid nodes. So that's the idea of the finding the features of the your prior space, prior knowledge. And so in this example, let's say this is domain with unstructured grid, and so this is boundary, and this is just no example mesh with the number of the element is around 3,000. But I just do the final meshing, oops, and make it around 700,000. And I use some kind of prior knowledge, covariance matrix in this case, on this structure, and do this kind of 700,000 by 700,000 matrix of the dense covariance matrix. I do the eigen so compression, and then find the 100 salient images. So this is basically image of the your data assimilation solution. So linear combination of this vector space will be the solution of your inverse model or data assimilation. And you can just see the first feature is some kind of global feature of the entire space. And you can increase the number of the feature, the high frequency, go to high frequency, and you can actually clearly see the variance, variability of your solution basis structures. So using this kind of the features, you can find the coefficient of this features. Then linearly combining this kind of features will give you some solution of your data assimilation without much loss of the accuracy in data assimilation inverse modeling. So in this case, using the hierarchical matrix or this compression technology, eigenvector analysis of the 700,000 by 700,000 dense matrix only took about 30 minutes in a modern desktop. So the idea is compression on the subset of your data set, then you can accelerate the inverse modeling. The second challenge is number of numerical simulations. Usually signal processing or WD people maybe just they also use a lot of the data assimilation and Kalman filtering or other kind of the inverse modeling strategy. But usually for the model is not the very expensive one. And in our science, on the other hand, so we usually run one simulation, like atmospheric in modeling. It would require about 1 hour or something like that, okay, or even 1 day for the simulation. Then typical inverse modeling data or simulation requires at least 100,000 or 10,000. So this is because you usually requires computation of the gradient information to have the some kind of the optimization of the your data misfitting, data data matching problems. And in this case, you need to construct or Jacobian matrix, which is gradient of the your Ford model simulation with respect to your state variable. And even you have really efficient Ford modeling Jacobian construction solver, which is so-called adjoint state method, and usually requires one iteration, number of observation plus one numerical model. You have to do that. Okay. So in typical standard data simulation problem, and this requires so if you think about the observation is like million, so you have to for some vanilla application, you have to do the number of million numbers of numerical simulation run. So maybe this will saturate your um, the high performance computing clusters. And again, once you construct this gradient matrix, Jacobian matrix, and then in the some estimation problem, you need to combine or computing with your prior knowledge with this kind of sensitivity matrix or Jacobian matrix. And this is also dense matrix multiplication problem, but this can be dealt with very efficiently with what I mentioned before about the compression algorithms. Okay, so the idea of this number of fold simulation, how we reduce this number of simulation is some active area research. So usually people is doing two kind of things. One is Kalman filtering. In this case, you use the ensemble Kalman filtering, where you are just generating a lot of this ensemble or realization or some scenarios from the covariance matrix, your prior covariance matrix, and you can calculate. You can just propagate this realization through your numerical model or Ford model, then calculate it. And this actually is approximation of this kind of dense matrix algebra. So with some kind of the statistical error, you can construct it with the ensemble Kalman filter. I don't want to just go into the detail of ensemble Kalman filter, but this is the idea of the ensemble Kalman filter with only about 100 numerical models instead of the number of observation plus one numerical models, you can achieve these kind of things. But the one caveat here is basically approximation of your covariance matrix with the ensemble. Then, so statistical approximation is usually very high errors. So one may think that this may be the ensemble Kalman filter or some kind of knowledge or this kind of approximation data simulation strategy can deal with the nonlinear features, but this is actually not. It's about some kind of byproduct from the sampling error from the prior distribution. So you have to actually be careful about the number of ensemble to have some guarantee the convergence to the actual distribution. Otherwise, it will actually give you some kind of divergence and other kind of the computation issues. And other approach might be you are just doing this kind of the compression algorithm followed by extraction of features. So this is so-called spectrum-based data simulation. So basically, idea is that you extract the eigenspace or subspace basis of this covariance matrix and propagate this basis through your numerical model and achieve like 100-fold model runs and calculate this important cross covariance or auto covariance of the distribution in your data simulation problem. So yeah, and then this kind of the ensemble Kalman filter and spectral Kalman filter approach is probably core or like advancement of the reducing number of the simulation tools, some number of simulations. So this is some kind of diagram of the technology. So this is just published from the our recent paper, Live paper, uh, in the same title, in Journal of Hydrology. If you are just interested, just refer to this paper. But idea is here. So inverse modeling data simulation. Usually, number of observations is really number of observations is really small in many cases. But if you have the number of observations is very large, you probably don't want to do the risk scale problem, maybe deterministic problem, kind of the data simulation. Otherwise, you have to count the uncertainty in a mostly Bayesian framework. And if number of degree of freedom, like a number of unknown, is smaller than 100, maybe you use the particle filtering or other kind of the some method that identify multimodal distribution. But otherwise, we have to have some kind of assumption of a Gaussian prior because it actually accelerates the problem. And even in so in practice, usually now we have a lot of the observations. So if you have the more observation, more information, so your prior analogy become more close to the Gaussian prior. So that assumption may be valid for your application. And once you have that, so if you want to do some kind of batch data inversion, so you can do inverse problem. You can solve the inverse problem. Otherwise, you want just sequential data simulation. You probably want to use Kalman filter. And if it is very expensive, you want to just do the eigen ensemble Kalman filter or eigen spectrum-based covariance compression will followed by fast linear algebra method, then you can accelerate all the this kind of data simulation within some kind of tractable computational time. Okay, so wow. Okay, so this is some sort of another example. I just mentioned about the subsurface engineering. So now I just move to the another application of the maybe people in Hawaii may be interested in this kind of application. So more like also the defense application. So this is called the bathymetric estimation. So given you have some sort of the wave characteristic of the surface of the near shore, can you identify the elevation of the bottom topography of your ocean or surface zone? So that's the very crucial for coastal application for like some sort of the like the army operations or navy operations, and also like a shipping operation, these kind of things. You probably want to know about the bathymetric profile. Okay, so in many cases, especially in Hawaii, usually people use the direct sampling and airborne lidar, so remote sensing techniques. And in the case, if you have very clear water, then this kind of remote sensing technique will actually give you very nice, very accurate estimation of elevation of this depth of the bathymetry. But in other cases, like you have a lot of the these white portions, like breaking waters, and also water turbidity is very high because of the microorganism and other things. Then so this LiDAR does not work, and as you know, direct sampling cannot be. So just measuring of the bottom depth is not available during the storm season. Okay. So what people usually do is just taking pictures from the tower of the static tower. So it's so-called Argus system. So this is the area of the North Carolina where tons of amount of the research was done in this area. And you just take a picture of the surface phenomena with snapshots every like 0.1 second or just 16 hertz frequency. Then based on all this information, you probably see that this kind of white region or breaking area, you should have some kind of sandbar. And so other area, you may have some kind of prior knowledge of the direct sampling. So you may actually construct this kind of parametric pitch representation based on your prior knowledge. And but this one may not work very well. And you have some sort of the direct sampling data and other things. And what people usually do is just using this image data. You process this image with their time series images and to calculate the wave characteristics like a wave speed or wave celerity and these kind of things. And you can use some hydrodynamic model and phase resolving phase averaging model and use some kind of inverse modeling. So basically, for the map is you take the boundary condition of the wave and also bathymetry elevation and use the hydrodynamic model, and you can actually reproduce this wave phenomena, wave propagation. Okay, then you get the wave information, wave speed and other kind of frequency and wavelengths. Then based on this one, invert this wave phenomena to get the bottom bathymetry. And this is quite important application for shipping operation and the defense operations, and to to um, access to some kind of the foreign country. Okay? And recently, so even a drone-based one is just used in this case. So you just deploy drone and capture the wave phenomena real time, and so using this information to get the wave speed, and then feed this one to the inverse modeling of data simulation to get to know what the topology of your bathymetry. Okay. So my application was just using this kind of the accelerate the data simulation, inverse modeling techniques, and do some kind of real-time um, estimation of bathymetry. So this is one application we had. So I am collaborating with the Army Corps of Engineer in Maryland, and so we have several sites in the North Carolina and San Diego naval base, and then so their drone actually captures or measures this kind of wave speed and also the inland elevation with the search for motions, and these kind of things are our observations. And so this drone has some, I believe, about the 30 minute to 1 hour flight time, and they are capturing all the wave information. So using this kind of information and pre-processing of the wave data set and feed it to the net, and so this is the some sort of the estimation result. So you clearly see this is direct survey because the area in North Carolina, they had a lot of direct survey with their the facility. So we know the true bathymetry elevations. And this is the inverse modeling result. And you clearly see with the allowance measurement of this is a pre-processed wave speed and the elevation, then you are just having very nice map of the so this estimation. And this only took about 5 minutes on the some workstation. So basically we want to just deploy this one onto the drone, and drone can just receive the real-time data. Then we just process and then transfer this one to the some remote server, and remote server you just run the inversion to get the very close to real-time bathymetry inversion. Okay. So this is some kind of data feeding or wave speed and inland elevation, which is great. And other kind of the parameter estimation is done here. And so one profile, so one location, I believe around this one. So you probably clearly see that this true direct sampling is quite consistent with the estimated one. And also the stochastic inverse modeling requires just to provide the range of uh, the your estimate or uncertainty, and they are just within the confidence interval, Bayesian credible interval, 95% interval, quite well. And you see that up to 400, we have some kind of information. Other than that, we don't have information because, and then there is some kind of discrepancy. So now I think I have only 4 minutes. So yeah, and this is some kind of advance in the traditional data simulation and inverse modeling examples. Then now we probably have more extension with some current emerging ideas in machine learning. So machine learning, especially deep learning neural network, so it's like now is some sort of the standard for the many applications. And this is because so previously the compression algorithm and other things is based on the linear theory. And this machine learning also just do some sort of the linearized methodology to optimize or calibrate this neural network, but it has some nonlinear component, and this actually enhance or accelerate or just improve the accuracy that traditional methodology cannot achieve. So several ideas like the dimension reduction or just compression using this kind of neural network to have more compressed like with some the small number of the bases or features than the traditional technology can achieve. Another one is the physics informed learning. So if I think about the neural network as and uh, recently this kind of the software product like PyTorch or TensorFlow, they actually have some kind of good capability of the automatic differentiation. And if you can approximate the underlying process or PD with neural network and automatic differentiation AD can do the calculation of Jacobian or gradient very easily or very conveniently, very efficiently. Once you just have the good approximation of the underlying process, then they can be actually used for the solving the PD and other kind of things. And so this probably not have I probably have time later about talk about this direction. And so if you are just interested in this direction, so you probably visit my webpage, and I'm chairing this AAA Spring 4 meetings of this physics informed learning, and there are some proceedings and there are some kind of results from other colleagues, then you might want to read this kind of information. And third one is I just briefly want to mention, and so use of digital twins. So digital twin is basically you have the some kind of the natural phenomena like the bathymetry and bathymetry problems. We in this case traditional learning or traditional inversion problem, we have to do some kind of processing to have a wave speed and inland elevation. What if we can use the neural network uh, and just using this kind of pictures or the images without any kind of pre-processing, just throw out this feeding this one as an input and get the output bathymetry. And this is idea is really great. You don't have need any kind of pre-processing and corresponding errors. The problem is the numerical model cannot handle this kind of information image. So any kind of PD can take the input of images and then just solve the problem and then give you output. And this image can be very affected by lights and other kind of light reflection. So but there is an area or growing this emerging area about digital twins. So you are just doing some sort of the very expensive numerical modeling or some kind of person modeling, and also consider account for the effect of the light and other kind of things. So that makes very similar to the natural observation. So one idea is like uh, some photorealistic numerical model. So this is so-called, I didn't mention here, but the Stellaris model developed by USC. And this model is very nice because this is very different from the traditional model because it is solving the Bouchnik type equation very efficiently, but it focuses on the lightning and light reflection and so orientation of sun and cloud and other kind of things. So this is some kind of snapshot of the result. This is some sort of the window-based model, so you can download it and run the simulation. So usually supervised learning about the machine learning requires input and output pairs. So we need some kind of the image from the drone and then also bathymetric result to have this inverse relationship or inverse map or inverse um, modeling. But usually we really don't know about we have a lot of the input data, we have a lot of the image data, but know about we don't know about the underlying bathymetry. But in that case, we can actually augment the data using this kind of digital twin kind of system. So we can actually generate a lot of the simulation that is quite close to the actual pictures, the drone taking pictures, then augment data, and we have a lot of it, data sets and do the inverse modeling. So this is recent work and published in remote sensing. I have to actually add this one here, but so you can actually come to my website and then download the papers. And this basically using the this image from the drone image or tower image, and you can this is true one, and you can actually see the estimation is quite close to truth with any kind of pre-processing and only based on the machine learning.
All right. Thank you, Dr. Lee, for such an informative presentation. Any questions from the audience? So actually, I have a question then. Because you mentioned, you know, the last few slides, I think you mentioned about the virtual environment. I'm curious about the, you know, those are 3D, you know, modeling software. I have used some before, like Blender and all that. You know, it's kind of like commercial software where that you can use to create the 3D realistic images and, animations. And they also have some sort of water simulations, you know, ocean simulations. Do you know anything? Do you know their approach? How realistic their simulations are?
I really don't know about the blend or something like that, but they probably use the was the SPH. So I don't remember the spherical particle hydrodynamics. And it, so
Yeah, particle. Yeah, they do. I think they use
yeah,
particle. Yeah.
yeah, that solver accuracy is quite I would say impressive. So we did a very um I mean relatively um, less computational cost, they can actually do the really nice simulation. And I believe it, their simulation is quite realistic because usually this kind of application doesn't require a lot of accuracy, right? So people usually, like ocean science, try to match the wave height and every second or something like that. But this one is just for generating image, realistic image. You don't really care about the like like 1 inch error or something like that. So this is basically compensated by the light reflection and other kind of things. And I believe some commercial software for this one, they are very consistent with the real observations. Or if you set up the numerical model, their model, um, reliable with some confidence.
Thank you. Any other questions?
Oh, I have a question. Hi.
Yep. Hello.
I guess this is rather naive. So I'm curious. So now we have a lot of sensors, right? So you basically, in whatever area you want to understand, you can just sprinkle a lot of sensors. But then if you can measure the area with tons of sensors, then you will not need mathematical models to right, like you wouldn't need it because you would just like you will basically know exactly what the behavior is without the sensors. So I guess I'm curious, like, is there like an optimal number of sensors, or do you know what I mean?
Yeah, you mentioned the pure data-driven approach. So where there is some sort of the area, there is no numerical model for prediction, or at least the modeling error is quite high, right?
Yeah, right. So something like that, right? Like, I mean, are we approaching that in terms of these type of applications? Are we approaching that threshold of pure data-driven models?
The data, it totally depends on the application to application. So if you just use a pure data-driven approach, yeah, usually it requires like a million data points or trillion data points. So based on your degree of freedom, or just the dimension of your manifold or space of your problem. So how do you want to just resolve the some sort of the phenomena, underlying phenomena? Yeah, you need. So I cannot say this one, but there are some sort of the I don't remember the name of the professor, but in maybe there is some sort of tradition, some analysis of the number of data set, how many number of data to do some kind of the reliable statistical prediction. But I cannot tell because if you know about the supervised learning type settings like input output pairs, that's great. Otherwise, if it's unsupervised learning, then you need more data, more than the data, and so anyway, you have to actually resort to some kind of physical relationship, or if there is something. But other than that, I have no idea. And so there is some kind of the in data simulation, so probably no Kalman filtering or other kind of particle filtering. So you can observe something, then you update your uncertainty matrix and to find the optimal number of the observations for your specific application. So this is optimal sampling problem or something like that. And so there's many application and technology out there, but I cannot tell how many data you need I need for the specific application. I really don't know. I know something in my area.
Okay, maybe because I have no knowledge of civil engineering, like what kind of things are like, because you showed that in the observations you have is like we're interested in concentration or pressure. Is that what I mean? Because I feel like those things are, you can place enough sensors to measure, right, exactly what the assume.
Oh, you can actually remote sensing and geophysics. You can measure some kind of indirect variable relevant to the concentration, also pressure. So you can use the electromagnetic, MT, magnetotelluric to estimate the subsurface structure, not high resolution, but up to the 1 kilometer to 2 kilometer. But you need some sort of more relationship. But they are all kind of indirect relationship, and we have some numerical model parametric relationship to convert this one to our quantity of interest.
Okay, thanks.
So I guess, if you think about traffic, right? So depending on how detailed information you want to pull, so you can measure individual, for example, individual vehicles on the road or individual pedestrians, and all the trajectory will be different, right? So you can also, depending on, I guess, how you look at it, how detailed information you need, I think you can certainly get a whole lot of, you can measure everything, and then you have a complete picture of the real from the real measurement. But I'm thinking the total number of sensors may have some relationship with the principal component analysis, I guess, right? If some of the sensor data may be redundant, maybe, because you can probably use some models to recover. I don't know. I mean, I'm thinking that it's probably case dependent and also somewhat subjective in my experience.
Yeah, I guess I'm not, I wasn't thinking about, yeah, so there's actually problem with physical measurements, right? Like you said, like if we need to use electromagnetic type of things to actually measure pressure or something, then that itself prevents, there's a granularity limit before the physical sensor can actually detect it.
Yeah.
But in terms of cars, I mean, suppose if everyone's car has the ability to connect to the internet, there is no ambiguity because you would, like a computerized system would know exactly where the car
That's
is.
right. That's right. Even if you use your cell phone, that actually cell phone is a mobile sensor, right? And that you actually everything will be kind of deterministic. You know exactly where they are, things like that. Yeah. But
Yeah,
I mean, whether that's needed, I mean, it's another question, I think, right? From model, you may be able to figure out some of the information without having the physical measurements.
but we don't have any physics-based models of human moving. Thankfully, we have physics-based models of how waves and I don't know, I guess dirt can move, but
Yeah,
as far as I know, there's no physics-based models.
yeah, that's right. Yeah,
That's interesting. Yeah, it's interesting how the
Well, like no agent-based modeling can probably approximately reproduce the behavior of the people. That requires a lot of computation cost.
I just worked on a agent-based model project. It was it was impossible.
Okay, maybe
I mean,
it's very complex,
yeah, I mean, especially if you only have partial measurements. If you just want to create a pure virtual world, that's no problem. But if you have partial measurements and you want to infer how the real world is, it was a needle in a haystack.
so years ago, NSF has a program called a NEAS program. I don't know, Harry, if you're familiar with it. So they actually supported research. Basically, it's kind of a hybrid simulations where you're doing some experiments, but also at the same time you only do half of the experiments, say a structure, and then the other half would be done in the cyberspace through computers. So you kind of feed the real data in real time into the real simulation. So that's kind of physical cyber combined study. I think that's something, I guess, I don't know if that's what you meant. You have physical measurements and then at the same time you have simulations for the entire system.
Yeah, I think so, right? Like that's what when you show that video of the coastline, but it was a computer simulation. That I assume that they were using computer models to get more data. I feel like for physics-based problems, that's not a bad approach.
Yeah.
It's, you know, I mean, because I
So
don't know.
Harry, sorry, Harry, I have another question. So for the technique you presented, is it applicable to like molecular simulations? I mean,
Yeah, MD simulation definitely.
right?
Yeah,
Yeah, I would
people are
assume.
using the any kind of the two-body problems, molecular simulations, and using this kind of techniques. So
Yeah.
hierarchical fast multiple methods, it comes from this kind of application. So
Yeah.
like galaxy simulation, two-body problem. Yeah, definitely.
So maybe I'll
And
talk to you. Maybe I'll talk to you sometime later. I'm actually trying to do something in that area.
Yeah, MD simulation. Yeah. So probably no, you want to contact Albert. Albert is just working on this kind of simulation, and he's very knowledgeable in that
Okay.
direction, molecular scale.
All right. Any other questions? I guess if not, then we'll end here. So we were 16 minutes over time. Thank you for bearing with us. Have a good weekend. And thank you, Dr. Lee, for this presentation. Very exciting.
Okay.
Yeah.
Thank you.
Thank you. Thank you, everyone. Bye.
Bye.